name is Christopher. I'm doing my research project on using geospatial analysis to find potential wind farms in Kansas, or wind farm locations in Kansas. So I know what you're thinking. Why Kansas? Because Kansas is known for its large open areas of untapped land, and as everybody knows, there's winds in Kansas. So there's been several considerations to take into account when building a wind farm in Kansas. Oh shoot. All right. There are so for this project we use ArcGIS and we use GIS data, geographical information systems, and we used the data of GIS data for that. And that came in vector data and raster data. Vectors are points, lines, and polygons. So points, lines, polygons. And it also comes in rasters, which are cells with values in them. Now there are considerations you got to take into account when building potential wind farms in Kansas. Specifically wind, because it's a wind farm. You want to look at that a spot and see whether or not the wind speeds are good enough for a wind farm. Another consideration would be land cover, which is whether or not you're building on top of a city or you're building on an empty grassland. You also don't want to build on a slope, or a slope that's too steep, because otherwise you need to spend more money and more resources to create a flat, buildable space. These are the absolute values that we're going to be working with. The other ones are proximity values, things that are close or far away that would be better to build next to. Things that we don't want to build next to would be wildlife protected areas, cities and towns, and airports. Things that we do want to build close to would be power lines, because we want to make sure that we're close so we can apply that energy to the power grid, and railroads and roads so we can get the equipment there to that plot. So the first thing that we classified was airports. Now, the FAA doesn't have specific regulations on whether or not turbines can be built near airports, but they do have regulations on building things over 300 feet near an airport. If you build, these are the airport points here in purple. So if you build within, so on runways that are 32,000 or 3,200 feet or more, you need a 20,000 feet buffer around it. If it's under 32,000 feet, you need a 10,000 foot buffer. As you can see here, the bigger circles are the 20,000, and then the smaller circles are the 10,000s. This is a binary system, so that means that we don't want to build in the black areas because it would take too much bureaucracy and paperwork to get through to build something there. So we decided to make it a little easier and make the black areas, the buffers, a no value, like a 0. And the white a buildable area. Another consideration was land cover. Like I said before, we want to build on something relatively easy to build on. Something that's not easy to build on would be like the red areas here. The red areas are cities or developed land. The blue, which is water, we can't really build on water. And the green, which are forests. It's really hard to build on forests because you need to clear it out and get it prepped for a wind farm, and that takes a lot of resources. Things you do want to build on top of would be things like the brown here, the cultivated crops, the white, which is herbaceous, or the yellow, which is hay and pastures. Now, when building wind farms, you got to take into account as well cities and towns. Now, people, I don't know why, don't really like walking out their back door and running right into a wind turbine. So they prefer to have it further away. So what we did is we took cities and towns, which is classified as a place that has a population of 300 or more, and we measured the distance away from them. White is closer to a city or a town, and black or darker color is further away from it. Now, distance isn't always bad. We also want to be close to things like power lines, because the closer we are to a power line, the easier it is to integrate it into the electrical system. This is our power lines here, and this is the distance away. Same with the cities and towns, white is closer to the power lines and darker colors are further away. We did that for railroads because we need to be able to get the equipment in for a fraction of the cost. And roads, which we can get equipment in as well. Now, we also need to take into account slope. Slope is, there's a big deal with slope. With the literature that I've read, it says that above 13% grade slope, we can't build very well because we don't want to terrace it and waste resources getting it flattened. So how we got our slope is we took the elevation data of Kansas, here's the elevation data, and we took two adjacent points and we measured the difference to give it a slope rating. This is the slope data here. The red is the higher slopes and the green is a flatter zone, a flatter area. Wildlife protected areas are also something we need to take into account. Similar with cities and places, or cities and towns, we don't want to be right next to them because people generally get pretty unhappy about that. So, same with cities and towns, we also took the wildlife protected areas and measured the distances from them. Now, we need wind to make a wind farm, so I went out to the National Renewable Energy Laboratories website and we looked for the GIS data. They had data on there, and thankfully they had it pre-classified. They've got it scaled on a 1:7 scale, and it's based on wind speed and wind power density. Now, the reason why wind turbines work well is because the faster the wind speed, the more power you generate on an exponential curve here. So this right here is our wind data, already classified for us. For the entire duration of this presentation, red is going to mean a bad place to build, and green means a good place to build. As you can see on the eastern side of Kansas, it's not so great. On the lower western part, a lot better. I'm going to point out that back here, it says a 7. There isn't actually a 7 in Kansas. It's more of a possibility, but there hasn't been a measure of a 7. So to get more precise data, I took existing wind farms, ones that were actually built and already constructed, and I looked at them. I got up close to see where the turbines were built because we couldn't find a data set that actually had the exact locations of the turbines. So what I did is I went up close with satellite imagery, and I saw that there actually were wind turbines. We took those and I clicked on every single one of these, making my own data set. I clicked on those 642 times. Yeah. That gave us more precise data because there was an actual space, there was an actual point in which we built it on. If you look here, the red dots are the wind turbines, and the way it was classified before was in these polygons. Now, when we're taking into account here, we need to know exactly where these turbines are built in order to know how to build our wind turbines. If you notice, there are spaces in between the points here, empty space, where there aren't turbines. We don't want that data. We want something that's precise and down to as close to the actuality as possible. After that, we use a thing called the near function. The near function takes input features, such as turbines, and measures the distance from it to a feature, a near feature, which would be a city, a power line, a road, something like that. So what we did is we took the turbines and we created these histograms. Now, if you look here, we took, right here, this is measured in kilometers. From 0 to 1 kilometer, we counted 134 turbines close to a power line. We did this down all the way with all of our turbines, we did this down all the way to our turbines to show the distances. If you can see here, we took this and divided it by, we took the smallest number and divided by everything to give us a score, a reclassification score. As you can see, 6 is a 1, and double that, the 12 is a 2, and then over here, the 4 to 5 kilometers, with the 48, it's an 8. Makes sense. Actually, confirming our hypothesis of being near to a power line, you can see here it's actually skewed to the right here, that we are actually correct in that we need to be close to a power line. So we took that and we applied it to all the layers. Now, land cover is slightly different because when I looked at land cover's numbers, turns out there are only turbines built on top of herbaceous, cultivated crops, and hay and pastures. Lucky us. So what I did is I took the land cover and turned it into a binary as well. I took the weight, and wilderness has a 10% weight. The reason for that is because slope is really consistent with this data, and wilderness protection areas wasn't. So we took into account slopes effect on the score more than we did with wilderness. This is our final picture. And final results. Let's took all our layers and put it into a composite layer. Black is the complete black is a 0 value. Darker colors are a lower value, and light colors are a higher value. I needed something to compare it to, so I made one that was equal weighted. That means that the considerations with those features all had the same power on the score. Now I needed to compare those two together. So we got a difference. The blue is where weighted has more power on or has more effect on the score, and the red is where equal weighted has more effect on the score. So what I did is I took the top 5% of weighted, and I took the top 5% of equal weighted, and then I combined them to see where they shared certain spaces. This here is where both equal weighted and weighted agree upon a certain score. And then I combine them together to get a look at it. As you can see, there's some blue outside of the purple. That's where where weighted thinks it's a good score, and then there's red here where equal weighted thinks it's a good score. And then I took the top 1% of available space for the top available big areas, big continuous areas, and looked at it. I put it over the 5%. This is my final spot. This is where I would build a wind farm in Fort County near Dodge City. These are the biggest polygons we have on top of the top 5%. This is the best place where I would build a wind farm. Here's my references. And I'd like to thank the 1979 FSI alumni, Kevin Lear and Timothy Frederick, for paying for me to come here and experience this wonderful thing, this wonderful research project. And I'd like to thank Christopher Erickson for helping me the entire way. Any questions?